In this lecture, we'll discuss about translations, dilations, and reflections. Both vertical as well as horizontal translations are going to be discussed. In dilations, we'll discuss both stretching as well as compressions. Let us begin with our familiar example, y equals x square. That is, our function f of x is given by f of x equals x square. We know the graph is the parabola. Now, if you are defining a new function, g of x, whose root is given by f of x plus 1, which means x squared plus 1 here, then what we are interested now is that can you plot the graph of g of x once you know about the graph of f of x? Because g of x is manufactured out of f of x by just giving the rule g of x equals f of x plus 1. Some easy observations one can make it. While drawing the graph of f of x, that is the points xy, where y is obeying x square, y equal to x square, we are getting the typical point 0, 0, 1 corresponds to 1, that is 1, 1, 2 corresponds to 4, minus 1 also corresponds to 1, 2 corresponds to 4, minus 2 corresponds to 4, etc. And we are getting the graph of y equals x square. But looking at g of x, what's going to happen is whenever you're going for the graph in the second situation, that is the graph of g of x, the y value is simply getting x square plus 1, that is already x square plus f of x rule. With that, just added 1, which means corresponding to 0, you have to lift 0 plus 1, you will get here. At 1, original f value was 1, so you have to add again 1, that is 2. Similarly, minus 1, 1 will be the f value, so 1 plus 1 will be given here. Such a manner, you are getting the lifting. So, what's going to happen is the following. If you are trying to draw the graph out of this, what one can observe is the following. You will get a shift. I mean a vertical shift of 1 unit. That is what's going to happen. So obviously the graph will look like this. So, which means once f of x equals x square, given function f of x equals x square, and we know the graph is this one, then g of x, which is given by f of x plus 1, is obtained just by simply translating the whole graph of f of x 1 unit up, vertically up, is what's going to happen. Instead of this constant 1, if I am putting 2, that is f of x plus 2, all the discussions will be valid and we are getting the parabola is shifted to 2 units up, vertically up. So in general, what's going to happen is, if f of x is given with us and g of x, we are making the rule as f of x plus a positive constant c, then the graph of g is obtained from f of x by vertically translating c units. So this was the case where c is a positive constant here. We have discussed vertical translations upwards. Now, instead of this f of x plus 1, if I am making h of x, for example, the function is f of x minus 1, then analogously we can define, while determining or plotting the graph of h of x, whenever x, y's are together, y is going to be h of x, then with the y values, we are just subtracting 1. Which means corresponding to the 0, originally 0 was there, that was shifted to minus 1. So very similarly, all the points are shifted downwards with 1 unit from the original situation. So what's going to happen is this one, we will get the graph of g of x just by shifting downwards. So h of x equals f of x minus 1 is going to have the graph of f of x which is shifted 1 unit downwards. That's the vertical translation but now it's in downwards motion. Generally, one can say this if g of x or h of x, whatever it may, is given by f of x minus c, is going to be the rule for g, where c is a positive constant. The graph of g is obtained from the graph of f by just translating it vertically down c units. These are the moral of the whole translation business, vertical. One can think about horizontal translations too. With the same example, y equals x square, if you are looking at. If y equals x square, that is f of x equals x square, the typical values one can write down, x and f of x, the table. Suppose I am looking at my new function g of x, which is going to be x plus 1 whole square. So the rule is nothing other than that f of x plus 1. And we are going to be interested how the graph of g, or it can be just plot the graph of g by just looking at the graph of f. Again, some observations are at ease. See, corresponding to 0, 1, 2, 3 or minus 1, minus 2, we are plotting all the points y's here. So g of x values are x plus 1 square, which means corresponding to 0, if I am looking at the g value, then I will be getting 1 square, it will be 1. For corresponding to the x value 1, I am going to get 4. Corresponding to x value 2, I am going to get 9. 3 corresponds to 16. And minus 1 corresponds to 0. Once again, minus 2 corresponds to 1. This is what is going to happen. So, what is the effect on the graph of g? See, corresponding to 0, f value was 0, that y value was 0. But g value is 1. That 1 is actually taken by f at 1. So, this 1 is shifted to 0, corresponding to 0. So, that is why you are going to get 0 corresponds to the y value 1. So, that will be the point 0, 1. Now, if you are looking at 2, x equals 2, f of x value was 4. Now, g of x value is going to be 9. Right? So, this 9 actually is taken by f at 3. So, that 9 is shifted to 2. Similarly, 4 is also shifted to the 1 correspondence. So, everywhere a backward shift in x is happening in the left side moment. See, corresponding to 0, I am going to get 1 here. So, this is the marking. And corresponding to 1, I am going to get g value 4. So, I will be getting somewhere here, which was originally taken at 2 for f. Now, if I am looking for minus 1, that corresponds to 0. So, again a left shift. Very similarly, I will be getting all other values like this. So, if I am just looking at the points and trying to plot it out, I will be getting the entire graph is moved left with 1 unit. So, what we can observe is the following. If f of x is x square and g of x is going to be x plus 1 whole square, which means f of x plus 1, then the graph of g is obtained from the graph of f by just shifting the whole graph of f 1 unit towards the horizontal direction left. So, translation left, the horizontal translation I am going to look at, and 1 unit left, it's going to happen. From the f, I have to move left 1 unit. So, if I am just writing h of x, for example, f of x minus 2, x plus 2, then the shifting should be again 2 units to the left. So, this is what is the effect here. In general, one can state and see and convince ourselves like this. If you are looking at, if you are given with a function f of x And if you know the graph of f of x, and if g of x is given by the rule f of x plus a positive constant c, then the graph of g is nothing other than the graph of f shifted to c units left horizontally. This is c is greater than, this c is greater than 0. One can just observe what will happen with the same example. If you are looking at y equals x square, and f of x equals x square, and if I am defining g of x equals something like x minus 1 whole square, which means f of x minus 1. One can easily see that the whole graph is going to be shifted 1 unit right, which you will observe this way. So that can be stated as follows. If g of x is defined as by the rule f of x minus c, where c is again a positive constant, the graph of g is obtained from the graph of f by just shifting c units horizontally right. Just shift c units right. So this is what the whole translation business, horizontal as well as vertical things, are going to happen. Let us consider one more example. This y equals x square, or f of x equals x square. Now look at the graph on the right hand side. I can just get this graph what's shown in the right side as follows. If I'm writing this is f of x equal, the first function is f of x equals x square. Suppose I'm making a rule g of x, which is going to be f of x minus 2. Then obviously the whole graph is shifted to 2 units right. This is what's going to happen. From this g, if I'm again making, see this by rule, f of x minus 2, if I'm going to write, means x minus 2 whole square. That is the whole effect. G of x is going to be x minus 2 whole square. So that is this graph. This is y equals x minus 2 whole square. Now, from here, if I'm just pushing 1 unit up through a rule, I may write h of x equals g of x plus 1. So it shifts 1 unit vertically up. So this will be an uplift actually. So g takes 2 units right, and again h acts on the 1 unit up. So the final map of, or the graph of h of x is this one. So obviously g of x was nothing other than that x minus 2 whole square plus 1. So the right hand side graph is h of x is the graph of h of the function h of x is given by x minus 2 whole square plus 1. Very similar examples one can try and convince ourselves. Now we will consider the effect of scaling. By this we mean we will consider g of x equals either c times f of x, or c is a real number, usually positive real number here, which gives vertical stretching as well as compressions. Now, if you are considering g of x equals f of cx, that is another way of scaling, then this amounts to us the horizontal stretching as well as compression. So these two things we are going to, these two situations we are going to discuss. So one can look at different cases for c. In the first case, vertical, this g of x is given to be c times f of x. In both cases, we'll consider c greater than 1 separately, as well as c is in between 0 and 1. These two cases will differ drastically, and let us see how the graph of g can be obtained from f. See, just looking at the graphs, this dark blue graph is x square graphs. This y equals x square. Now if you are making it 2 times x square, that is g of x equals c times x square. C is 2, so greater than 1. Then what you can observe is the graph is this yellow graph that is just stretched upwards. That is the effect here. X square is transformed whenever you are considering 2x square, it is just stretched vertically. Now on the other hand, if you are just looking at c equals 0.5, that is 1 by 2 for example, that is g of x equals half x square, then what you can observe is you'll get the graph as shown by the red line, which means it is actually shrinked or the compressed vertically. So the whenever you are considering g of x, which is c times f of x, and if c is greater than 1, then we can obtain g from f by a vertical shift. I mean vertical stretch, not shift actually, vertical stretch. If c is in between 0 and 1, then g can be obtained from a vertical compression. So vertical stretch as well as vertical compressions are going to happen like this manner. The other kind of scaling, for example, g of x equals f of cx, that will give horizontal effects. Look at the various graphs here, x square. This blue graph is about x square. The yellow graph is 2x whole square. So c times x whole square, c is greater than 1. So a horizontal compression is going to happen. It's on this way. And if you are considering the red graph, that is red graph is corresponding to half x whole square. This actually stretching that x square graph horizontally. So whenever g of x equals f of cx, if c is greater than 1, then we can expect a horizontal compression. So it will just compressed horizontally. If c is in between 0 and 1, we will get a horizontal stretching effect. These are the natural things what you can expect by scaling. Once it is understood well, even with a nice wave function or somebody can look at examples. See, for example, this graph is about sin x. So the first sin x, if you are making into 2 times sin x, so our g of x is c times f of x, c is greater than 1. Obviously, we can expect a vertical stretching. If you are considering half times sin x, that is half is now in between 0 and 1, so we will get a compression in the vertical level. On the other hand, if sine 2x is concerned, then horizontally a shrinking can be expected from f is sine of x. And if you are making sine half x or sine x by 2, you will get obviously a stretching the horizontal level. These are the various effects one can try it out. We will conclude this session with a discussion of reflections. So with a given function f of x, let the graph will be y equals f of x here. And if you are just looking at the function defined as g of x is given by minus of f of x, then one can easily plot the graph of g from f. See, in this case, see at 0 we are having 2. Correspondingly, the rule is the y value for g has to be given minus 2. So, it will be marked here. 1, you will f value is here. Just the negative of that thing will be downstairs here. At 2, you may have here f value. So, you have to revert it into minus of that value. Everywhere the same thing is going to happen. So, all together you will get the graph as the yellow graph what you are going to get. So this is the graph y equals actually minus f of x. All the y values are given to be negative. So it's clear that this is just a reflection on the x-axis. So whenever you are thinking that the x-axis is a mirror, y equals f of x is get reflected on this x-axis and you are getting below here like that. So the effect of g of x equals minus f of x is that it is giving us a reflection with respect to x-axis. Just here to reflect it with respect to x-axis, you will get that. Now, on the other hand, a change like this, for example, g of x is going to be f of minus x, then we are going to get a reflection with respect to y-axis. That's also obvious here, because at 1, see, this is my y equals f of x. So at 1 I am going to get here, my rule is f g at x is going to be f at minus x. So for the g value, if I am searching corresponding to the negative input, you have to give it for f and look at the value. So at this one, if I am interested what should be my g value is, I have to look for f at minus 1. So f at minus 1, I'm getting it here. So that has to be given here. So the entire graph is going to be getting a reflection like that. At 1, I'm going to get my value 0 because f value is here. Now at 0, once again I'm going to get here. Now if I'm looking at a minus 1, at minus 1, to get the value for g of x, I have to look at what happens at f value at 1. So f at value at 1 is here. So that I have to plot it here. So it will come around here. So altogether, the same thing is happening everywhere. So I will be get the function reflected like this. So I will be getting like that. So that is the yellow graph here is shown to be g of x equals f of minus x. So we will be getting a reflection. So g of x equals f of minus x will give us a reflection with respect to y-axis. So you have to consider y-axis as the mirror and you will get reflected here. That is what is generally reflection is going to do.